So good morning to one and all. So in the previous class, we are discussed about the digital storage oscilloscope, the principle of digital storage oscilloscope, and what are the main operating principle and what are the main blocks are present in the storage digital storage oscilloscope we have seen. And today's class we will see the electrostatic deflection of CRT. Electrostatic deflection of CRT. So how the electrons which are produced from the electron gun will be deflects on the beam on the screen of the CRT. So that will be seen here. So first of all, we'll go for the electrostatic deflection. So what is the electrostatic deflection? Electrostatic deflection is the method of aligning the path of charged particles by applying the electric field between the deflecting plates. So here, after the electron gun will releases the electrons from the gun, so those electrons will be moves through the deflecting plates, horizontal deflecting plates and vertical deflecting plates. So how this electron beam will be changes its path or alignment of these electrons will be decided by the field, electric field, which is applied between these deflecting plates. Okay, so the potential which is applied on the deflection plates, depending upon that, the beam of electrons will be changes its direction, so movement. Okay, so in this lecture we will see how the electron which is moving through the vertical deflection plate, how it will be deviates its deflection. It means its movement, how it will be changes. Okay, so for that we have to find the deflection of the electron beam. So this figure shows the this is the electron which is entered into the deflecting plates. So this is the these are the plates. Okay, and through this, when the electron is entered in this particular deflecting plates, we will apply the deflecting voltage. So depending upon the potentials which are applied on these two deflection plates, so here we are applying a deflection voltage of ED. Okay, and the length of the each plate is LD. Okay, and the distance between these two plates is D. Okay, the distance between the two plates, deflection plates, is the D. Okay. Okay, so whenever the electrons will be entered into this particular deflection plates, so it will be experiences some accelerating. Okay, due to the applied potential, the electrons which are entered into this plates will be experience some acceleration, and due to that acceleration, so it will be changes its velocity. Okay, and whenever these electrons will be moves out of this particular plates, deflecting plates, the how much velocity it is there, and in such direction it will be moves. Okay, so once these electrons will be comes out of the deflection plates, and in which direction it was deviated, in such direction only it will be travels to the screen of the CRT. This is the screen of the CRT. Okay, so here we have to find how the deflection will be. So how much deflection will be possible by the deviation of the electrons. Suppose the electron is entered at a certain velocity. Okay, and when that velocity is entered with certain velocity, so with the application of the potential on these deflection plates, how much variation of the electrons will be possible in these plates. Okay, so if suppose there is no potential is applied, then what happens? The electrons will be travels straight line. if there is no potential or zero potential is applied on these deflecting plates, that causes the electrons beam or electrons will be travels at a center of the screen. Okay, straight line, like a straight line, they will be moved. Suppose we are applied some positive potential on the deflecting plates, that causes, because these are the electrons and we are applying some positive potential on this both the deflecting plates, and due to that, so this positive potential will attract the electrons, and depending upon the amount of the potential we are applying on this plates, the attraction force will be depends, and according to that there is a movement of the electrons that leads to increasing of the velocity. Okay, and depending upon that, how much amount of deflection is possible on the screen of the CRT will be decided. On the screen of the CRT will be decided. Okay, so that deflection will depends upon the direct proportional to the applied potential. Okay, so that we are going to conclude finally. Okay, the deflection which is obtained at the screen is directly proportional to the applying voltage on the or potentials which are applying on the deflection plates. Okay, so that we will see derived in the equation. The next slides. Okay, this is also shows the same picture. So this is the screen, and these are the two deflecting plates. This is the one. Okay, so these are the vertical deflection plates. These are vertical deflection plates. Okay, and the distance between is the d, and the total length of the plate is this is LD. Okay, not TD, it is LD. Okay, so that we will see by deriving the equation. So generally, the figure shows the electrostatic deflection. Okay, so two plates in between this electric field where the between which the potential difference is applied. So here we have a deflection plates, two deflection plates A and B. So consider the A and B. Okay, two plates, and in between we apply the electric potential. Okay, potential difference, and by that these deflection plates produce the uniform electrostatic field in the y direction. So here we are using vertical deflection plates. So we are considering vertical deflection plates. That's why the deflection of the beam will be in the vertical manner, not horizontal manner. Okay, the electrons will be moved vertically. Okay, the electron enters between the plates, experiences some force only in y direction, and the electrons will move only in that direction. Okay, so once the electrons will be enters into these deflection plates, those electrons will be moves in the y direction only. So here we have x direction is nothing but the horizontal direction, y direction is nothing but the vertical direction. Okay, so the electrons will be moves in the vertical direction because we are explaining the movement of the electrons in the vertical deflection plates. Okay, we are consider the vertical deflection plates. That's why the electrons will be moved vertically up and down. Okay, and there is no force either in x direction or z direction. Hence, no acceleration of electrons occurs in that direction. Okay, so there is no force in x and z directions. So considering E naught. So E naught is the voltage of the pre-accelerating anode in volt. Okay, E is charge of an electron. All of you know that it is in terms of coulombs. M is mass of electron, that is in kgs. Vox is the velocity of the electron when entering into the deflecting plates. So velocity of the electrons which are entering into the deflecting plates, that is considered as V naught of x or Vox. And ED is the potential between deflecting plates. ED is the potential between deflecting plates in volts. D is the distance between deflecting plates. D is the distance between the two deflecting plates. And LD is the length of the deflecting plates. And L is the distance between the screen and the mid of the deflecting plates. So capital L is the distance between the mid of the plates. This is the mid of the plate, this point, half of the plate, and to the screen, the distance between the mid of the plate and the screen, that is the capital L. And LD is the length of the deflection plates, and the small d is the distance between two plates, and Vox is the accelerating velocity, okay, so which is entering into the two deflecting plates. Okay, and D is the deflection of the electron beam on the screen in the y direction. So this is the deflection of the electron beam on the y direction on the screen, in the y direction in the screen. Okay, so first we will see, so when the electron moves from the accelerating cathode to the anode, they lose their potential energy. Okay, so actually these electrons will be generated from the electron gun. Okay, and from there those electron cathode, okay, so those electrons will be travels through the accelerating cathode and to the anode. Okay, accelerating and for accelerating anodes and focusing anodes will be there. Okay, and through that the electrons will be moves and they lose their potential energy. Okay, and the formula gives the potential energy is the E into EA. That EA is the accelerating energy. Okay, acceleration potential. This is acceleration potential. Okay, and the electrons gain the kinetic energy, and their energy is given by equation of mv square, whereas v is nothing but the v is the velocity of the electrons which are entering into the deflection plates. Okay, here the velocity of the deflection plates is the entering into the deflection plates. Okay, v naught of x. So here the loss of energy and the gain of energy, so both are equal. Okay, so equating these two energies, we will get the velocity of the electron when it enters the deflecting plates. So that is we will get 2e square root of 2e ea by m. The velocity of the electron in x direction remains same. So here one thing, velocity on the x direction is remains same. Okay, because no force was in the x direction. So that's why the electric field in the y direction is Ed by d. Ed is the potential which is applying on the deflection plates, and d is the distance between the two plates. And the electric field intensity in the y direction is F is equals to E into epsilon y. E into epsilon y. So epsilon y is the Ed by d. The force acting on the electron in y direction, F is equals to m into ay. M into ay. So here we will equate this force. Okay, so E into ey. E into ey. So from this m into ay is the force, is equals to the force electric field intensity, that is equals to E into ey. And from that we can get the ay. Okay, acceleration of the electron in y direction. So the initial velocity of the electron enters into the deflection plates is equals to 0. Okay, and there is a displacement of the electron in y direction. Okay, so that is y is equals to of at square. Okay, and from this we can get, by substituting the ay in this equation, we can get the half of the E into epsilon y into by m by t square, where at time t. Okay, so the velocity in x direction is constant, and the displacement of the x direction is given by x is equals to v naught of x into t, and from this t is obtained as x by v naught of x. And substituting this t value in the previous equation, we can get the displacement in y direction. So y is equals to half of the E into epsilon y by m into t square. So where t is equals to v x by v naught of x. The above equation represents the parabola. Actually, this equation is nothing but the formation of the parabola. So from this parabola equation, we can get the slope. We can get the slope. So slope is nothing but dy by dx. So dy by dx. With this we can derivation of this y equation with respect to x. With respect to x, we will get this equation. Okay, and by substituting the x is equals to LD. So LD is the deflection plate's length. Okay, in the place of x, overall we are getting the x value in terms of LD. Okay, so that is we get the value of tan theta. So tan theta is nothing but the here. So in the diagram we have, so tan theta is nothing but the d and here we have a length, so L. Okay, so that is the in terms of, so 1 into, so y. Okay, so in the vertical direction it is y by, and x is in terms of LD. LD is the x. Okay, so with that we can get this tan theta. Okay, after passing through the deflection plate, the electrons move into the straight line. So once these electrons will be came out of these deflection plates, we can flow the electron in the same direction. Okay, straight line. Okay, and this straight line is the tangent to the parabola at x is equals to LD, and it intersects the x-axis at point O. Okay, so we are saying that the straight line is the tangent to the parabola. So see, so here the once these electrons will be releases from this deflection plates, and these electrons will be travels in the same direction, and when we draw a straight line to this particular parabola, so this will form as a parabolic area. Okay, parabolic formation of the electrons. The electrons will be moved as a parabolic. So okay, so when we draw a straight line from this draw a tangent line to this particular curve, we can get a line. Okay, and that line will cuts the center of this particular, the center of the beam. Okay, and it is exactly half of the length of the deflection plate. Okay, where this line will be crosses the a point. Okay, x-axis line. Okay, and that particular line is exactly half of this particular length of the deflection plate. Okay, half of this deflection plate. So so that is obtained. So by using these equations, and tan theta is equals to y by x, we can obtain that value as LD by 2. From the previous equations we can get this LD by 2. So it is just half of the where that tangent line will cross the x-axis, I mean deflection plates, half of the deflection plate will be obtained. Okay, the apparent origin is that the center of the deflection plates. Okay, and the deflection D on the screen is expressed as, the deflection D on the screen is expressed as D is equals to L into tan theta. L into tan theta. So from the obtain the tangent triangular. So this deflection is nothing but, so this deflection is nothing but, so this is the L, and this is the D, this is the D, and this is the capital L. The distance between from the screen to the half of the deflection plates, and with this we have a theta. Okay, so the angle is this, and from this we can get the tan theta is equals to D by L, and from the deflection D is obtained as tan theta into L. Okay, so tan theta and L. So here we have, so from this previous equations we will substitute the tan theta. From the previous equations we will substitute the tan theta in equation, we substitute the tan theta value in L into tan theta, and from this we will apply this equation. Okay, and so this is the D. So by substituting the value of V naught of x, so here V naught of x, it is in terms of the x-axis. Okay, so the velocity of the electrons which are entering into the deflecting plates is the V naught of x. Okay, and whereas V naught of x is obtained in previous equations, and that is substituted in this equation. The V naught of x is derived, V naught of x is substituted here. Okay, so that is nothing but m by 2e into capital EA. Okay, so by cancelling, so we will get the L into ED into LT by 2 into D into EA. L into ED into small ld by 2D EA. Okay, so from this equation we can say that generally this capital L is constant. Okay, and capital small ld, so this is the length of the deflection plates is constant, and 2 is constant, and D is the distance between the two plates is constant, and this acceleration EA is also almost constant. Okay, so and the deflection which is dependent upon, or it will be directly proportional to the deflecting potential. So the potentials which are applying on the deflecting plates. The deflection of the electrons beam which is moving in the vertical deflection plates will depends upon the potentials which are applying on the deflection plates. Okay, similarly in the horizontal deflection plates also same situation. Okay, so in place of vertical movement, it is moves in the horizontal direction. Okay, so like this the deflection of the electron beam, or the beam of the electrons will be moves on the screen of the CRT will depends upon the potentials which are applying on the deflection plates. Okay, if the deflection potential is the applying deflection potentials, so from where we are applying these deflection potentials? From the vertical amplifier. For the horizontal deflection plates, we are applying from the horizontal deflection amplifier. Okay, so for the both the deflection plates, we are applying the potentials according to that applying potentials. Okay, applying nature of the potential on these deflecting plates, depending upon that, the movement of the electron beam will be changes. Okay, that will be effect on the variation of the beam on the screen. Okay, suppose we are applied more amount of the positive potential on the vertical deflection plates, then what happens? The more movement of the electrons will be there. Okay, so electrons will be deviated more effective, it will deviated. Okay, like that, the potential is decreased. I mean, amount of potential applied was very small. Then according to that, the beam will be changes its direction in y direction, in the direction of y. Similarly, in the x direction also. So according to that, in the x direction, so it will be changes its movement. Electron movement will be changes. Finally, it will displace on the screen based upon the potentials which are applying on the vertical and horizontal deflection plates. Okay, so from this we can say that the deflection is directly proportional to the D, that is deflection potential or deflection plates potential, the potentials which are applying on the deflection plates. Okay, and from this D, okay, so from this deflection, so we have two more derivations. So that is a deflection sensitivity. Deflection sensitivity. The deflection sensitivity of a CRT, the deflection sensitivity of a CRT is defined as the deflection of the screen per unit deflection voltage. Okay, so what is the main sensitivity is nothing but sensitivity is nothing but the applying voltage. Okay, sorry, output to input. Generally, we can consider the sensitivity. So for given input voltage, how the output is responding. Okay, output to input. Okay, from here, what we are applying the potential. So we are applying the potential to the deflection plates. So from that, what we are obtaining deflection. Okay, so for a given amount of the potential we are applying, our voltage is applying deflecting voltage we are applying, and how much variation, so how much deflection is possible on the screen. So that is defined as deflection sensitivity, because it is the final output is the deflection and the input is the applying deflecting voltage, applying voltage. So what you are applying on the deflection plates, so that is the input. So output is the deflection and the input is the deflecting voltage. That voltage causes the deflection of the beam on the screen. Okay, so here it is the ratio of it is the deflection of the screen per unit deflection voltage. For a unit voltage, for a unit voltage, suppose 1 volt or 2 volts, for change of the 1 volt to 2 voltage, how much deflection is occurred? For a change of 1 volt to 2 volts increase of the voltage, how much variation of the deflection is occurred on the screen? So whether it is 1 centimeter or 2 centimeters. Okay, so that particular ratio will be obtained as a deflection sensitivity. So on the screen we will get the in terms of the screen in terms of centimeters. Okay, so here the in terms of meters. Okay, we can convert the centimeters into the meters. Okay, so SI units, we can consider the SI units. Okay, so meters per volts. Okay, deflection in terms of meters. So deflection sensitivity is SA is equals to D by ED. Okay, and next one, so by substituting D and ED. Okay, so here ED and deflection voltage, that is deflection voltage on the numerator and deflection voltage on the denominator, with both will be cancelled. We can get L into small ld by 2D into capital A, capital EA. Okay, so this is the sensitivity. Once you know that deflection formula, and from that we can get the sensitivity, deflection sensitivity. And another one is deflection factor. Another one is deflection factor of a CRT is defined as reciprocal of the sensitivity. Deflection factor is inverse of the sensitivity, deflection sensitivity. So deflection factor G is equals to 1 by S, and that is equals to inverse of this one. We'll get volts per meters in terms of volts per meters. Okay, so in the examination point of view, so they are asking the questions based upon these deflection sensitivity and deflection factor. So most of the cases they are asking the question on these only. So that we will see some questions are here. So if you consider the example 21.8, so I am reading if you are not visible. So calculate the maximum velocity of the beam of electrons in the CRT having a cathode anode voltage of 800 volts. Assume that the electrons to leave the cathode with zero velocity. Charge of electron is 1.6 into 10 to the power of minus 19 coulombs, and mass of electron is 9.1 into 10 to the power of minus 31 kgs. So all of you know these values. So we have to find the maximum velocity of the beam of electrons. Okay, having a voltage of anode voltage of 800 volts, and assume that the electrons to leave the cathode with zero velocity. And from the equation V naught of x, from the V naught of x, we can find the velocity of the electrons in the x direction. That is the square root of 2 into E into E A by M. So here 2, and E is the electron charge 1.6 into 10 to the power of minus 19, and EA is the applied voltage, okay, cathode and anode voltage of 800 volts, and M is the mass of the electron 9.1 10 to the power of minus 31, and from this we will find the velocity of the maximum velocity of the electron beam. And next one is so this question 21.9 example 21.9 is asked number of times. They are asked this question, this problem, okay, number of times. It is very easy question. Okay, so from the previous derivation we can have to remember the velocity of the beam equation and deflection sensitivity equation. In some cases they also asking the deflection formula. So once you know the deflection formula, or you can remember the deflection formula, so from that we can find the deflection sensitivity and we can find the deflection factor. So this example is an electrically deflected CRT has a final anode voltage of 2000 volts. So final anode voltage of 2000 volts, and parallel deflecting plates 1.5 centimeters long. So deflecting plates are having 1.5 centimeters long and 5 millimeters apart. So it is 5 millimeters apart means the distance between the two deflecting plates. And this is 1.5 centimeters is the plates length. Okay, long length of the plates. If the screen is 50 centimeters, from the center of the deflecting plates, so this is nothing but capital L. If the screen is 50 centimeters from the center of the deflecting plates, it is the 50 centimeters. That is nothing but value of L, capital L. Find the beam speed, the deflection sensitivity of the tube, and the deflection factor of the tube. So they are asked for 3 parameters: beam speed, the deflection sensitivity, okay, deflection sensitivity of the tube, and deflection factor of the tube. The velocity of the beam is nothing but square root of 2E into EA by M. Okay, and from that we can obtain this for 26.5 meters per seconds. Okay, and from equation, deflection sensitivity equation, So capital L, LE and 2D into A. So from that we can obtain the sensitivity is 0.375 millimeters per volt. So they may be asked in terms of meters also. So you may convert this millimeters into the meters. Okay. So for a unit applying voltage, there is a 0.375 millimeters of deflection is obtained for a unit change of the voltage. The electron beam will be deflected. Okay, deflect this much of distance. Okay, 0.375 millimeters of distance is possible for unit voltage application. So this voltage is applying through the vertical amplifier and horizontal amplifiers. When we apply the for the vertical amplifier, we are applying from the input signal. So for the input signal corresponds to there is a change in the application of the voltage on the deflection plates. And according to the applying potentials on the deflection plates, the electron beam will be deflect on the screen of the CRT. Okay. And deflection factor G is equals to 1 by S, and that is equals to inverse of the deflection sensitivity. And from this we can get the 2.66 volts per millimeters. And similarly, CRT has the anode voltage of 2000 volts and parallel deflector plates 2 centimeters long and 5 centimeters apart. The screen is 30 centimeters from the center of the plates. Find the input voltage required to deflect the beam through 3 centimeters. Okay, here they are asking the how much input voltage is required to deflect the beam through 3 centimeters. Suppose 3 centimeters deflection is required, then how much voltage we have to apply? So that is the